Ever wondered how the aroma of a brewing coffee reaches your senses even when you're several feet away? That's a question with an answer rooted in the fascinating world of mass transfer. It's not just about the enticing scent of your morning cup of joe. It's about how a drop of ink disperses in water, or how a waft of perfume spreads in a room. If you've ever marveled at the sight of a beautiful sunset, that too is a product of mass transfer, as different gases in the atmosphere scatter light in various directions. How does our body regulate its temperature? You guessed it, mass transfer is at play here too. It's this ubiquitous, yet often unnoticed process that makes our world function the way it does. The process that makes this happen is called mass transfer, and it's something that affects more aspects of our lives than we might realize. Now let's dive straight into the heart of the matter. What exactly is mass transfer? In the most basic terms, mass transfer is all about the movement of molecules from one location to another. This typically happens when there's a difference in concentration, temperature, or pressure. Think about it this way. Imagine you're in a room, and someone sprays perfume at one end. After a few moments, the scent permeates the entire space. That's mass transfer in action. The perfume molecules move from a region of high concentration, that is, the spot where the perfume was sprayed, to an area of low concentration, which is the rest of the room. It's important to note that mass transfer isn't only limited to gases like in our perfume example. It also occurs in liquids and solids. Picture a sugar cube dissolving in a cup of tea. The sugar molecules move from the cube, where they're densely packed, into the tea, where there's less sugar. This is another illustration of mass transfer. Mass transfer is a fundamental concept in many scientific disciplines, including physics, engineering, and environmental science. It's vital in various processes such as distillation, evaporation, drying, and even in our bodily functions like breathing and digestion. Understanding the principles of mass transfer can also help us to tackle real-world challenges. For instance, it's crucial in developing efficient and sustainable methods for water purification, waste treatment, and energy production. In the grand scheme of things, mass transfer is a constant and natural process that governs many aspects of our daily lives and the world around us. It's the invisible engine that drives the movement of molecules in gases, liquids, and solids, shaping our experiences and the environment in ways we might not even realize. So, mass transfer is all about how molecules move from one place to another, whether in gases, liquids, or solids. Now, how does this mass transfer happen in gases and liquids? Let's find out. Molecular diffusion, in simple terms, is the movement of molecules from an area of high concentration to an area of low concentration. Picture a drop of ink in water. Initially, you see a concentrated spot of color, but give it time, and the ink molecules spread out, creating a uniform hue throughout the water. This is diffusion at work. In gases and liquids, the process is the same. Molecules are always in motion due to thermal energy, and this constant motion results in a continual mixing and scattering of molecules. This is why the smell of freshly baked cookies can waft from the kitchen to your room upstairs. The aroma molecules are diffusing through the air. A few factors influence this molecular diffusion in gases and liquids. These include the size of the molecules, the temperature, and the medium they're in. Larger molecules move slower and hence diffuse slower than smaller ones. Higher temperatures mean more kinetic energy, leading to faster diffusion. And finally, diffusion in gases is generally faster than in liquids due to the greater space between gas molecules. This diffusion process is not just a random walk, it's guided by fixed laws of diffusion. The first law states that the rate of diffusion is proportional to the concentration gradient, or the difference in concentration between 2 points. The second law takes it a step further, explaining how diffusion causes the concentration to change over time. In essence, molecular diffusion is a dance of molecules. They move, they mix, they scatter, all driven by their inherent kinetic energy and the concentration gradient. It's a fundamental process that underpins everything from the smell of a rose to the functioning of our lungs. So, we can see that diffusion is a key part of how molecules move around in gases and liquids. But what happens when these molecules move between different phases, like from a gas to a liquid? Here's where the theories of interphase mass transfer come in. Interphase mass transfer is a phenomenon that is as fascinating as it sounds. It's the process by which molecules move from one phase to another, like from gas to liquid or vice versa. This isn't a simple process, but rather a complex dance of molecules, controlled by a few fundamental theories. Let's start with the film theory. This theory visualizes a stagnant film of fluid around the interface, where the mass transfer is happening. It's like an invisible barrier that molecules must cross to go from one phase to another. The thickness of this film along with the concentration difference across it, controls the rate of mass transfer. The thinner the film and the greater the concentration difference, the faster the mass transfer. Next, we have the penetration theory. This theory offers a dynamic view of mass transfer. It suggests that eddies or turbulent flows in the fluid bring fresh molecules to the interface, which then penetrate into the other phase. The time these molecules spend at the interface is called exposure time. The rate of mass transfer depends on the exposure time and the frequency of these eddies. The surface renewal theory is another interesting idea. It combines elements of both the film and penetration theories. According to this theory, the surface of the fluid is continuously being renewed by eddies, similar to the penetration theory. However, like the film theory, it also considers a stagnant film at the interface. The rate of mass transfer is determined by the frequency of surface renewal and the thickness of the stagnant film. Lastly, let's talk about the boundary layer theory. This theory views the interface mass transfer as a process occurring within a boundary layer. It considers both molecular diffusion and convective transport, which are influenced by the velocity and concentration gradients within the boundary layer. These theories, though seemingly different, all aim to describe the same process, the movement of molecules from one phase to another. Each theory brings its own unique perspective, helping us to understand the complex process of interface mass transfer from different angles. But why does this matter? Well, understanding these theories allows us to predict and control mass transfer in various industrial and natural processes. From distillation in chemical industries to gas exchange in our lungs, interface mass transfer plays a crucial role. These theories provide us with a more detailed and nuanced understanding of how mass transfer occurs between different phases. They help us to comprehend and appreciate the invisible dance of molecules that's constantly happening around us and inside us. So the next time you see a cloud, remember, it's not just water vapor. It's a beautiful demonstration of interface mass transfer, governed by these fascinating theories. So, we've covered a lot of ground today. We've ventured into the fascinating world of mass transfer and its critical role in the environment around us. We've explored how it's a fundamental process in various scientific and engineering fields, from chemical engineering to environmental science. We delved into the concept of molecular diffusion in gases and liquids, a phenomenon that's often unnoticed, but incredibly vital. We learned how molecules move from regions of high concentration to lower concentration, and how this process is influenced by factors like temperature and pressure. It's a constant, unceasing dance of molecules, happening right now, all around us, and even inside us. And then we journeyed to the theories of interface mass transfer, understanding the principles that govern the transfer of mass between different phases. We dissected the two-film theory, penetration theory, and surface renewal theory, each with its unique perspective on how mass transfer occurs at the interface of two phases. We've seen how these theories help us understand complex processes in industries, such as distillation, absorption, and drying. They've provided us with the tools to predict and control mass transfer in various systems, leading to more efficient and sustainable processes. So what's next? This is just the tip of the iceberg. The world of mass transfer is vast, with plenty more concepts to explore and understand. We'll be diving into more detailed discussions, practical applications, and even the latest research in our upcoming videos. If you're intrigued by what you've learned today and want to delve deeper into the mysteries of mass transfer, then stick with us. Join our community of curious minds eager to learn and understand the world around them. Subscribe for more because you won't find me later. We've got plenty more fascinating topics to explore together.